Alright, so definition of a horizontal asymptote: the line of y is equal to b is a horizontal asymptote if the graph of the function y is equal to f of x, if either the limit as x approaches infinity of f of x is equal to b, or the limit as x approaches negative infinity of f of x is b. So rational functions, or two polynomial functions divided, should have the same horizontal asymptotes in both directions. I've not run into a function that doesn't have more than two, to be honest. Alright. So, horizontal asymptotes on rational functions are actually pretty nice. We talked about this a little bit last year. It's actually the same chart as last year. So, for the rational functions, I'm going to have just my lead terms. I've got ax to the m over bx to the n, where m is the degree of the numerator and n is the degree of the denominator. The n behavior model can be looked at or written as ax to the m over bx to the n, or a b over b times x to the m minus n, because you always go top minus bottom. We can use the n behavior models of rational functions to identify the horizontal asymptotes of the functions. So it's kind of like our version of a little tiny cheat sheet. If you'd like to think about it that way, that's perfectly fine. Alright, so scrolling down, you guys are turning the page. If f of x is equal to a x to the mth, and g of x is equal to bx to the n, then f of x divided by g of x takes on three different forms. So one way to consider this is that if m and n are equal. So if I have m and n equal, so I've got basically ax to the m over bx to the n, and then if these exponents are the exact same, all that that's going to do is cancel out those x's, leaving me with just a over b. Alright, so as x would approach infinity or negative infinity, your end behavior should approach, whoops, I don't know why I put two different, a over b, because that would be your horizontal asymptote. Alright, what if my degree is larger than the denominator? So what if n is bigger? So I'm still going to have that n behavior model of ax to the m over bx to the n. So this time I would have like a x to the third over bx to the sixth, for example. So I'd have three more x's in the denominator than I would in the numerator. So that was simplified to a over bx cubed, where I have more x's in the denominator. So basically what I did is I would have to say, okay, I've got a over b times x. Oh my gosh, this is so tiny to do this. Let me back up a step. So I'd have to do a over b x cubed minus 6, because remember, you always do top minus bottom in terms of exponents, which would get me a over b x to the negative 3, which is why that would put me back in the denominator. So in general, all I'm going to do is I'm going to have a over b times x to the n minus m. So, since I have more x's than denominator, that means that my denominator is going to get bigger and bigger and bigger, while my numerator stays constant the whole time, which means that as it grows, it's actually going to get smaller, which means that as x approaches positive or negative infinity, your y should approach 0, kind of like all the way up here. My denominator grew faster while my numerator stayed the exact same. It will approach 0 because my denominator gets larger. Alright, so my horizontal asymptote in this case is just y is equal to 0. Alright, so what if my degree is larger than the numerator? Well, I'm still going to have that same end behavior model of a x to the m. Oh my gosh, okay. A x to the n over b x to the n. is equal to, this time I'm still going to subtract, so I'm still going to end up with that a x to the m minus n. Oops, I don't know why that subtraction symbol looks like it's an underscore. All over b. Or you can just write it right beside it. I don't really mind. But this time, if the numerator is bigger, that means that I'm going to end up with more x's in the numerator anyway. So I'm just going to go ahead and extend that over just so we don't have to keep writing it and keep writing it and keep writing it. So as x approaches infinity, well, if my numerator is growing faster, that's an uh-oh. Because then I'd have like 1x over 3. And then each time I get bigger and bigger and bigger, I'd be like, okay, well, that's 2/3. That's getting bigger. That's 3/3. That's now 1. And then I'd plug in bigger and bigger numbers for x. And I would see that my values aren't approaching just any one number. It's just going to grow larger and larger and larger and larger and larger. And that's no bueno for us. So as x is approaching infinity, y is also approaching infinity. Well, I guess it depends on which infinity it goes to, depending on your fraction. So in this case, there wouldn't be a horizontal asymptote, which is kind of a pain in the asymptote, because now we have to look for something called a slant asymptote. Alright, and what that's going to involve, why I say it's a pain in the asymptote, is because, well, that's going to involve long division, which I know many of us do not prefer. But, I mean, unless you're given a linear term on bottom, you cannot use synthetic division. You have to be given a linear term with a plain old x. You can have nothing in front of your x in order to use synthetic division, which is why it becomes such a pain in the butt. Alright,